Hey everyone. In this video, we're going to look at one of the fundamental equations that we use when we're thinking about gases. It's called the ideal gas law. Now, if you've taken chemistry before, you've probably already seen this equation. In physics and in science in general, it's generally not possible to model something exactly as it is in real life. We always have to introduce some simplifications. The ideal gas law is one such simplification. An ideal gas is just a gas that behaves according to the ideal gas law. Now, no gas in nature actually behaves this way, but many gases behave approximately this way, and so it's useful for trying to understand how gases behave. The ideal gas law looks like this. It relates the four main quantities that matter for a gas together: pressure, volume, the number of moles, and the temperature. The equation just says that the pressure times the volume, which is equal to an energy, will always be equal to the number of moles times the ideal gas constant times the temperature. But what is the ideal gas constant? Well, it's actually secretly something that we've seen before. The ideal gas constant is just equal to the Boltzmann constant multiplied by Avogadro's number. The reason is that when we're thinking about gases, we're often thinking about moles of gases. That's a pretty standard measure that we'll use for gases. When we want to think about the thermal energy of a substance, we need to know something about the number of modes that each particle in that substance has. When we're thinking about thermal energy, the Boltzmann constant also pops up. So the number, Avogadro's number, times the Boltzmann constant is really common when thinking about gases. This number, by the way, is equal to 8.314 joules per Kelvin. The ideal gas law just tells us how certain things will change. For example, if you imagine a system where the volume remains constant, if you increase the pressure of the gas, the ideal gas law says that the temperature must also increase. If the left-hand side of the equation is increasing, the right-hand side of the equation must increase as well. R is a constant, it can't change. N is just the number of moles of gas that you have, which most likely will not be changing. So the only thing on the right-hand side that can change is temperature. We'll get lots of opportunities to practice working with the ideal gas law. But it's just an equation. You can just use algebra in all the ways that you know how to do in order to solve for something interesting. For example, let's say that we know that the temperature of a gas is remaining constant, but the pressure is increasing. The ideal gas law says that the only way for this to happen is if the volume decreases. If the volume were to increase or stay the same, then the temperature must also increase as well in order for the ideal gas law to be true. The ideal gas law is one of the fundamental equations of thermodynamics. If you're given a problem and you're expected to treat the gas as though it behaves as an ideal gas, the problem will just say, this gas behaves as an ideal gas. If you ever see that, you can know immediately that you need to pull out the ideal gas law. Now, this can start to teach us some interesting things about the way that gases will behave. For example, in this course, we've talked a lot about heat capacities. In the last few DLs, we've actually built a model for the heat capacity of a gas. But specifically, we've actually built a model for the heat capacity of a gas at a constant volume. The reason for this is that if the volume of a gas isn't constant, then work is being done either on the gas or by the gas. Any energy that you add to a gas that's volume is allowed to change is going to be split between two places. Some of that energy will in fact go to increasing the temperature of the gas, but some of it's going to go to expanding the gas, doing work on its surroundings. If instead you're dealing with a system where the volume of the gas is constant, well, then none of that energy is going to expand the gas. It's all going into the thermal energy of the substance. And so you have to add less energy to a gas at a constant volume to increase its temperature than you do if the gas is at a constant pressure. Now, the ideal gas law doesn't care whether pressure or volume is constant. It just works as long as the gas is, well, ideal. But we can, of course, use it for constant volume and constant pressure processes, just as we can for any other process. If you use the ideal gas law and sort of relate that information to work, you get the following equation. It says that the specific heat of a gas, specifically an ideal gas, at constant pressure is equal to the heat capacity at constant volume plus N, the number of moles, times the ideal gas constant. Again, let's think about why this is the case. If you add energy to a gas and declare that the gas must remain at a constant pressure, the ideal gas law says that the volume of the gas must increase. If you add energy to a gas, its temperature is going to increase. And so, if the pressure must remain constant, the volume must increase, according to the ideal gas law. If the volume is increasing, then work is being done. Some of the energy that you're adding to the gas is being expended to increase the volume of the gas instead of going into increasing the temperature of the gas. And so the temperature change of the gas is going to be less than if that same amount of energy was added to the same gas, but the gas was held at a constant volume. This tells us that the heat capacity of the gas will be greater. Adding the same amount of energy results in a smaller change in temperature. And so heat capacity, which is just equal to the amount of energy we added divided by the change in temperature, well, it will be greater. In DL, you will actually see the derivation of how we get to this relationship between heat capacity and constant volume and heat capacity and constant pressure. It's not critical that you understand and memorize how to do this derivation. I'm not going to ask you to say reproduce it on an exam, but it is critical that you understand why the heat capacity at constant volume and the heat capacity at constant pressure are different. It just comes down to work and the way that gases behave. Now, all this talk of pressure and volume and temperature and all that might be getting a little bit overwhelming. There's a lot of things going on in gases, and it can be hard to keep track of everything. But thankfully, there are tools that have been developed to help us do this more easily. Unsurprisingly, these tools end up being graphs, and we're going to start to see in the next video how we can use graphs to figure out interesting things about a way a gas will behave. That's all for now. See you then.